In section 710, we'll look at the theory behind the gas laws we've worked with so far. Specifically, we'll examine the postulates of kinetic molecular theory and talk through how they apply to each of the gas laws. Let's begin. Up to this point, we've really only worked with the gas laws as mathematical relationships describing the behavior of gases. But why do the gas laws work? To understand that, we have to talk about the kinetic molecular theory, which explains the gas laws and some properties of liquids and solids. The first postulate states that gases are composed of small particles that are in constant random motion, meaning they travel in straight lines in any direction until they hit something. The second postulate states that the gas particles themselves take up almost no volume compared to the overall volume of the container. The third postulate tells us that the forces between gas particles can be ignored, and the fourth postulate tells us that collisions will be perfectly elastic, meaning the gas particles will bounce off each other without experiencing friction or any other loss of energy. The fifth postulate tells us the average kinetic energy of the gas particles is proportional to the Kelvin temperature of the gas. So how do these postulates back up the gas laws we've seen so far in this chapter? According to postulates 1 and 3, the particles of gases are in constant motion and are colliding with each other and with the walls of their containers. The force of those collisions is the source of gas pressure, as discussed in section 7.1. When the volume of a gas sample decreases without a change in the number of particles, the rate of collisions of those particles with the container walls must increase, causing pressure to increase. This is another way to state Boyle's law from section 7.2. According to postulate 5 of kinetic molecular theory, when the number of particles is held constant, an increase in temperature causes gas particles to have more energy and move at higher speeds. As these faster moving particles strike the walls of the container, they cause the container to expand, maintaining a constant pressure. This lays the groundwork for Charles' law, which we discussed in section 7.3. When the number of moles of a gas are increased, the rate of collisions of those particles with the walls of the container increases, causing the volume to increase while maintaining a constant pressure. That sounds an awful lot like Avogadro's law from section 7.5. In section 7.7, we saw how Dalton's law of partial pressures depends only on the number of moles of each gas particle, not on the identity of those gas particles. The postulates of kinetic molecular theory all support this assumption, especially postulates 2 and 3 that assume the particles take up negligible volume and experience no intermolecular forces. Let's see how well the assumption that the volume is negligible holds up with a quick calculation. Let's consider the volume occupied by 1 mole of water at 100 degrees Celsius and 1 atm of pressure in the vapor state and the liquid state. In the vapor state, we'll use the ideal gas law to solve for volume. V equals nRT over P, and dropping in the numbers, we see that our volume is going to be 30.6 liters. In the liquid state, we'll use the molar mass and density as conversion factors. 1 mole of water times 18 grams per mole times 1 milliliter over 0.958 grams of H2O, which is the density of water at 100 degrees Celsius, equals 18.8 milliliters. If we compare the volume that water occupies in the condensed liquid phase to that of the vapor phase, we see that 18.8 milliliters divided by 30,600 milliliters equals 0.06%, meaning that of the 30.6 liters of volume taken up by the vapor phase, only 0.06% of the volume is made up of the actual gas particles. The kinetic molecular theory explains why real gases don't behave like ideal gases. The first problem comes from ignoring the volume of the gas particles. While the volume the particles take up is very small, as we saw on the last slide, it is not zero. When these particles are compressed under very high pressures into very small volumes, the volume of the particles can no longer be ignored. Very low temperatures also cause a problem because low average kinetic energy allows the particles to slow down enough that they experience the intermolecular forces presented by other particles before whizzing past them. We'll discuss these deviations more fully in section 712, but for now, know that real gases will behave more like ideal gases at higher temperatures and lower pressures. High temperatures will mitigate the intermolecular interactions, and low pressures allow gas particles to take up a smaller volume proportionally to the volume the gas sample occupies. Here, I'll leave you with the parting thoughts of the authors.